Okay, welcome to EE 380, Spring Stanford Computer Systems Lab Colloquium, Spring 2019-2020, the year of the COVID. I'm Andy Freeman, and the other course organizer is Dennis Allison. Most museums are paintings. Other visual arts like dance, plays, etc., have their own display media, and so most museums end up being paintings. But the museums I always liked were technology artifacts, cars, coal mines, submarines. Now you know the museum I'm talking about. Trains, tractors. I grew up in a farming community where there was actually a tractor museum. But the most important technological artifacts of the last 50 years are computers. However, computers visually tend to be fairly boring outside of 1970s and 80s movies. And the other problem with computers is that they're tools, and their owners, once they cease to be useful to their owners, they just discard them. They don't pass them down to other owners who need less or aren't willing to pay as much. And there's no collectors. So they essentially disappear, or they just basically disappear, which makes collecting them into museums, which is a very good way of educating future people, getting people interested, is incredibly hard. Today's speaker, Len Shustek, has solved that problem. So without further ado, you're on.
Great. Well, thank you, Andy. I am Len Shustek, and I'm the chairman of the board of the Computer History Museum. And if you haven't been there, you should take a visit to it because it's just down the street. It's over on Shoreline and 101. Now, of course, right now we are closed because of the pandemic, but we're hoping that pretty soon we will open up again. Let me give you 30 seconds of my background so you can understand how I came to this odyssey. I was born and brought up in New York. I went to the Polytechnic Institute of Brooklyn, got a master's and bachelor's in physics. Polytechnic, by the way, is now NYU's engineering school. And then in 1970, I changed everything about my life, went to Stanford, changed my field of study, and enrolled as a graduate student in the relatively new computer science department, which then was a graduate-only department and was part of the Humanities and Sciences division of the school, not the engineering school. I eventually had a great time at Stanford and at SLAC, escaped with a PhD, went to Carnegie Mellon, was on the faculty there, computer science for a little while, came back to Silicon Valley, and over a period of 16 years did 2 different startups, both in the networking field. And one of them, the second one, was relatively successful. So I decided to retire, semi-retire, and go back to my first job, which was teaching. So this time at Stanford, I started teaching. None of this background qualifies me to start a museum of any sort, yet it happened. Here's what happened. If you look at the Stanford online calendar, catalog, you will see a course listed as EE 282 Computer Systems Architecture. It's basically the fundamentals of designing computers. Many of you have taken it or will take it. It talks about architecture, instruction sets, processor technology, memories, I/O, system software, virtualization, and so forth. I happen to be very familiar with this course because I took it 50 years ago when I first got to Stanford in 1970-71. I don't remember which quarter. And then it was taught by legendary professor of EE, Edward McCluskey, famous for all sorts of techniques for designing computers, including something you probably don't learn about anymore, the Quine-McCluskey minimization algorithm. But it's still at the bottom of Verilog and VHDL is the way they compile what you design in high-level language into detailed gate designs. So I remembered this course, and in fact, 25 years after I took it, it was the course that I taught in the winter quarter of 1994. Now, these 3 different versions of the same course separated by 25 years had some things in common, had very many implementation details that were different, and the focuses were different. When I taught it, it was designing microprocessors. When Ed McCluskey taught it to us, it was the design of mini computers. And when it's being taught now, notice that it says notebooks, smartphones, and data centers. That's fine. The fundamentals are still the same, and you are all learning how to design computers. When I taught it, it was with the beta test version of the Hennessy and Patterson classic, now classic, textbook, Computer Architecture, a Quantitative Approach. Compared to what I taught 25 years earlier, there was one important difference. Most of the history had been erased. When Ed McCluskey taught us about, for example, virtual memory and paging systems, he distributed to us the original papers from Tom Kilburn and others at the University of Manchester describing the Atlas computer, which at the time was the most powerful computer in the world. It was a transistorized computer with a whopping 16,048-bit memory, words of memory, could add at 500,000 adds a second, and it was the first machine that had virtual memory. I thought it was a fascinating way to learn technology, to understand where it came from. So one of the things I started doing when I was teaching was to spend the first 5 minutes in a kind of show and tell moment, bringing in old artifacts like this. This is a piece of Gene Amdahl's PhD thesis at the University of Wisconsin. He was a PhD in physics, but he decided that he wanted to design a computer, and he did. It was called the Whisk. And this is a piece of his computer built out of vacuum tubes, which some of you may not know ever existed or what they do. This module is probably one flip-flop. So this is one bit of information. So I found that the students were interested, at least in 5-minute sections, in history. And I decided, as a result of that, that something needed to be done to introduce history. I wasn't going to change the curriculum at Stanford. So I thought my contribution to this problem would be to start a museum. Look, we ought to learn about the history of our field. If you're a physicist, you learn about Newton and Einstein. If you're a chemist, you learn about Lavoisier and Boyle. If you're a biology major, you learn about Mendel and Darwin. Why don't computer science and electrical engineering students learn about Hollerith and von Neumann and Eckert and Hopper and all of the great people who created our field? So my crazy idea was to start a museum. There were several advantages. One is we've all had the problem of having people come to Silicon Valley and say, show it to me, show me Silicon Valley. And what do you show them? You drive around and you can see asphalt parking lots and concrete tilt-up buildings. How come, if we're the center of the world for computing, that there isn't a computer museum in Silicon Valley? So I decided I would start one. It was a totally nutso idea. I knew nothing about starting or running a museum, but I started writing white papers. This was the first one from October of 1995. I started shopping the concept around. I tried to get people interested in the idea, and many were. And I realized quickly that the important thing was not about collecting artifacts. Andy talked about the difficulty of collecting objects. That's true. But a museum is not a repository of objects. It's a repository of stories. So I want to take a little brief detour now and talk about an example story of the kind that I wanted to preserve and present, and we do preserve and present in the computer museum we eventually built. It's actually the most embarrassing question that people ask us. Who invented the computer? Everybody knows who invented the airplane and the phonograph and the light bulb. How come you don't know who invented the computer? You know, you ask some young folks and they'll say, well, maybe it was Steve Jobs or Steve Wozniak or Bill Gates. And of course, none of that is true. The problem is it's a difficult question to answer. It's a complicated story. But if you put me up against a wall and say, you have to choose one inventor of the computer, who is it? That's my answer. This handsome gentleman, Charles Babbage. He was the son of a wealthy banker living in London. He didn't have to work for a living. He became the Lucasian professor of physics at Cambridge University, which was the position that Isaac Newton had had. And he spent his time thinking about things. One of the things he did in doing his mathematics was to compare all of the different texts that gave mathematical functions. In those days, if you wanted to find out a sine or a cosine or a logarithm, you didn't compute it. That was very tedious. You looked it up in a book where it had been pre-computed. And he compared all of these books, and they all differed. On at least every page, there were some differences. And obviously, one or the other or both of them were wrong. And at one point, he said, "I wish to God these calculations had been executed by steam," which was a metaphor. He meant it was some way to do it mechanically with precision and accuracy so that you know the results would be correct. And he devoted the rest of his life to designing machines that would do things like that, to precisely calculate mathematical functions. It was an easy way to do sines, cosines, and logarithms. You can approximate them with a high-order polynomial equation. You can use the method of differences once you start with the first few values of computing subsequent values. So here's an example. This is a second-order polynomial equation. The second difference is a constant. So the way to compute the next value of the function for x equal 40 is just to do two additions. Easy. So Babbage decided he would build a machine to do this, a calculator. Now, the technology available to him at the time was not electronics, it was mechanics. So he designed something he called the difference engine. He began in 1823 to calculate by the method of differences sixth-order polynomials using 16-digit numbers. This was not an analog computer. This was a decimal digital calculator. That little wheel down there is an example of how he stores one digit. It's a rotating brass wheel that can be in one of 10 positions, indicating what the value of that number is. It also, in his design, had a complicated printing mechanism because he didn't want the result to have to be manually transcribed and typeset, because that introduces the possibility for errors. So he designed this machine. Now, how did he do it? You know, nowadays when we design machines, we use CAD, computer-aided design. Well, Babbage had his own kind of CAD. It was cardboard-aided design. These are original pieces from Charles Babbage of cardboard mock-ups showing the kinds of parts he needed to build in order to create his machine. So he designed it. He went out for funding to build it. He got funding from the only venture capitalist of the day, which was Queen Victoria, who gave him 17,000 pounds, that's about $2 million worth of money today, and said, "Go build it." Well, what happened? He spent the 17,000 pounds, ran out of the money. It took him 19 years. He built about half of the parts, the 25,000 parts that his machine would have needed. And he got into fights with his craftsmen. He wasn't good at managing people. So the result was a total collapse of the project, and his calculator was never built. Now, one of the reasons was that his eye was not on the ball anymore. While he was building this, he had a better idea for something else he wanted to build. This happens to engineers all the time. Instead of finishing the project they're working on now, they want to work on version 2 or some better project. And Babbage's better project was a computer. He called it the Analytical Engine. This is a top-down view of the engine he would have built. Each one of those circles is a tall column of those digit wheels, like we saw before. So this would have been a huge machine, the size of a locomotive. All mechanical, no electronics, powered by a steam engine. It was a computer that we would recognize today. It had a separate CPU, which he called the mill. It had memory, which he called the store. It had pipelining so that you could have multiple instructions in progress at the same time. It had parallel processing, so you could do multiple things at a time. It had conditional branches, so you could decide what to do based on the result of a prior calculations. It had loops, it had microcode so that you could encode complicated things with one instructions. And he had invented things that we reinvented 150 years later, like carry look ahead, sophisticated math algorithms. It was an amazing machine. It also, of course, had software. You had to program it. He did not put the software in memory. Instead, he put the software on punched cards. These were cards that he had seen used since the beginning of the 1800s by Jacquard on looms to automate the weaving process. And he had the idea of using those cards to encode the instructions that his computer would follow. Well, how do you make a loop? You connect one end of the cards to the other end of the cards in a big loop, and then it repeats over and over again the same set of sequences. Now, this was a great design, which Babbage did not publish. He worked alone and had no collaborators. He only had one collaborator, an unlikely one. It was this woman, Ada Lovelace. She was the daughter of the poet Lord Byron, estranged from his wife. And Ada's mother decided that in order to keep her from going crazy like her poet father, she would be tutored in mathematics. And she took correspondence courses from famous mathematicians of the day, like Augustus de Morgan, famous for de Morgan's laws. Now, this was extremely unusual for a woman to be involved in science in the 1800s. But she did it. She was brilliant. She worked on the programming, if you will, of Babbage's Analytical Engine. Now, she wasn't really the world's first programmer. Babbage had never yet designed the instruction sets. What she did were things like this with Babbage. This is an execution trace of a program that would run on the Analytical Engine to compute Bernoulli numbers. So it would be easy to imagine what the program would have to be to create that sequence of operations. She published when Babbage did not, translated an Italian description of Babbage's machine, and worked with Babbage on refinement of the machine in order to support these kinds of calculations. Babbage was entirely focused on mathematical computation. One of the things that Ada Lovelace saw was that it could be used for more than that. At some point, she said it might act upon other things beside number. The engine might compose elaborate and scientific pieces of music. She even foreshadowed AI. At one point, she said, "It does not appear to me that cerebral matter needs to be more unmanageable to mathematics than sidereal and planetary matter. I hope to bequeath to generations a calculus of the nervous system." She wanted to understand how the analytical engine could be used to create intelligence. None of this ever happened because Babbage never even attempted to build his analytical engine. So was Babbage a nut? Did he design machines that could never have worked? Well, 150 years later, the London Science Museum found 20 pristine drawings in the archive done by Babbage of a machine that he designed after the analytical engine. It was a simplified version of his original difference engine. And this fellow, Dorrance Wade, curator of computing at the London Science Museum, decided to see if Babbage was a nut. Or was he a brilliant engineer? He took Babbage's original drawings, worked for 17 years to build 8,000 pieces of iron, bronze, and steel, using exactly the same manufacturing techniques that Babbage could have used, built a machine 11 feet long, 7 feet high, weighs 9,000 pounds. This cost several $1 million, about the same as Babbage burned through 150 years earlier. And this is the result. The thing on the right is the microcode, if you will. It's the cam stack that controls the machine. The crank on the side is what powers it. There are 31-digit decimal numbers in stacks along those vertical columns. And the thing to the left is the printing machine that automatically creates a printing plate. And the thing works perfectly. The London Science Museum actually built 2 of these machines. We had one of them on display at the Computer History Museum for 8 years until it went back to its owner, who had paid the several $1,000,000 to have it built. Now, why did Babbage fail? Clearly, his difference engine, built exactly the way he designed it, works perfectly. Maybe his analytical engine would have worked had he built it. There's a project now to investigate whether we could build it. Had that happened, we would have had computers 100 years earlier than we did. We would have had a computer in 1848 instead of 1948. So why did Babbage fail? It wasn't for lack of brilliant engineering. There are many reasons, one of which is he didn't know how to organize the project and run the company. Does this sound familiar? There are probably 25 companies within 20 miles of Stanford who are going to fail because they have brilliant engineering and don't know how to manage the project, create a product. Now, Babbage almost had someone who would do that. Ada Lovelace wrote to Babbage in 1843 saying, "If I am to lay before you in the course of a year or two explicit and honorable propositions for executing your engine, would there be any chance of allowing myself to conduct the business for you?" She's basically offering to be the CEO of his company. And he turned her down. Who knows why? Maybe he, didn't trust the idea of a woman doing it. I think it was in large part because Babbage was bullheaded and wouldn't have accepted anyone in that position. In any case, Babbage died a bitter and disappointed old man. Nothing he had ever designed was a success. He said at one point, "Another age must be the judge of my talent." And we judge his talent. In engineering, A+, in management, F. I said none of his inventions had ever succeeded. There was only one. It was this. It was the Cowcatcher, the thing in front of a locomotive that pushes cattle off the track. But that's not the legacy he wanted to leave to us. So I think this story is a great story, and these are the kinds of stories that I wanted the museum to be able to tell. So I was going to go off and create a museum. First thing I did was to look around for other examples. So I traveled the US and the world looking for examples of computer museums. I found great examples of technology museums, in Chicago, the London Science Museum, the Deutsches Museum. I figured surely there must be some. If you look at how many other technology museums there are thousands of railroad museums and automobile museums and aviation museums. And I discovered there were no computer museums. This is a picture of all the computer museums before 1980. There was only one exception, and that was a museum that Gordon Bell had started in Boston. Now, Gordon Bell is a legendary computer architect. He was head of engineering at Digital Equipment Corporation for many years, responsible for the PDP-8, PDP-11, the VAX, and so forth and so on. He wrote a great book called Computing Structures, Reading and Examples, which reprints many of the papers about historic computers. And he decided he wanted to see somebody collect all of those computers. That was fact one. Fact two is the machine on the lower right is Whirlwind. It was a legendary machine built at MIT. They discarded it. Gordon called up the Smithsonian saying, "This is a international treasure. It needs to be preserved." And the Smithsonian said, "We don't collect computers." So Gordon said, "I'm going to have to start a museum of my own." So inside of Digital Equipment Corporation in 1979, he started a computer museum. Had a museum store, had exhibits, had problem getting funding. Digital, thanks to Gordon, was paying for it. But obviously, if it was called the Digital Computer Museum, which meant Digital Equipment Corporation, they couldn't get anyone else to finance it. So they moved. They moved to the wharf in Boston, right next to the Children's Museum, in front of the big milk bottle. They created a computer museum that ran from 1984 to 1999. They had exhibits. This is a diorama showing the UNIVAC 1 computer. They had programs. This is a list of the programs going on in 1982, I think it was. They started the Fellows Awards, giving honors to important pioneers. That's Grace Murray Hopper, who received the first such award in 1983. But the problem was that by the 1980s, much of the computer industry had left Boston. So it was in Silicon Valley. They had a hard time getting funding. They began to morph into a kids museum, which is a fine thing. They had a big walk-through computer where kids climbed over giant replicas of personal computers. But it wasn't the history museum that Gordon wanted to start. And they were in trouble. It was clear that they weren't going to survive. All of the good stuff, most of the good stuff, was no longer on display. It was in the back room, and Gwen Bell, Gordon's wife, who ran the museum, would give you a private tour. I said, okay, that's sad. So I returned to Silicon Valley, kept planning, learned lessons from the Boston Computer Museum, I thought. And then I got a call from Gordon Bell, who said, I have a deal for you. Don't start your own museum. Restart what we tried to do in Boston. Join the board of the Boston Computer Museum to start a West Coast outpost, which reinvigorates the original history mission. And that's what we did in the winter of 1997. Now, my first objective was to preserve the artifacts. They were one-of-a-kind things that could no longer be collected again. I managed to finagle some free space from a friend who was running a technology center at Moffett Field under the aegis of Ames, NASA Ames. These are World War II vintage Quonset huts with leaky roofs. Notice the sandbags in front of the doors on the right in the shadow of the big dirigible hangar that still had its skin on in those days. And we commissioned 7 huge tractor trailers to move the artifacts out of Boston to California. I didn't quite have the authority to do that, but I figured possession was 9/10 of the law. I wanted these things to be preserved, so we moved them. Sometimes a little hokey. We didn't have a forklift that could drop down this piece of the sage, so we backed 2 trucks back to each other and lowered the tailgates in synchronization so that we could get the machine down to the ground. It was an amateur effort, to be sure. We even moved objects into the dirigible hangar. I managed to get a forklift license and move some of the stuff around. I think I'm the only computer science PhD in the world with a forklift license, at least as far as I know. We started polishing and inventorying what we got. There was no inventory of these objects. There were thousands of things. What is this stuff? We didn't really know what a lot of it was. But we created a little exhibit called Visible Storage, where basically we set up all of the equipment or the stuff that was interesting looking and let people tour around. It had not a lot of labels. It was just stuff. It was great for the cognoscenti. People who knew what they were looking at loved it. It wasn't the museum I was dreaming of building, but it was a step in the right direction. We got some press. This is an article in the San Francisco Examiner about our efforts to build a museum. So one of the questions is where to build it. I had some conversations with folks at Stanford, which were tantalizing. Mike Keller, who I think is still there, head of the library, said, why don't you build it on Stanford campus on the opposite side of Palm Drive from the Cantor Arts Museum? So we would have arts on one side and technology on the other side. It's the location where the Bing Performance Center is now. I thought that was a great idea. So I talked to the chairman of the board of the Stanford trustees, and he said, great idea. If you've got 20 or 30 years to make that happen, go for it. I didn't. Try number 2 was at NASA Ames at Moffett Field. NASA was going to develop a research park. This is their conceptual plan of the research park. In red, it circled Computer Museum. They were going to give us 3 acres right in front of the big dirigible hangar to build our museum. It was going to be a land lease from the government. They were inside the hangar going to create a California Air and Space Museum. Sounded like a tantalizing prospect. We did an architectural competition. We had foam core models built of the building we were going to create. It was great fun. We were headed into the trap that many museums fall into of putting our emphasis on building a building instead of building a museum. Well, there were three things that happened that saved us from that trap. One is, of course, that the Boston Museum closed, so we were now free to do whatever we wanted. We were our own California corporation. The second is we realized pretty quickly that NASA moves with the speed of a federal bureaucracy. And we were startup people. We wanted to move more quickly than that. Their research part, which 25 years ago they had that wonderful plan for, is still in progress. And maybe someday they'll build it. The third thing that happened in about 1999, 2000 was the dot-com bust. Up until that time, there were no buildings available in Silicon Valley. They were all full. And suddenly, there were lots of see-through buildings, buildings that had been abandoned and were available. Like this one. This, at the corner of Shoreline and 101, was the sales and marketing headquarters of Silicon Graphics, famous computer company at the time, founded by Stanford professor Jim Clark. And it was empty. Silicon Graphics had sold it to a developer. And I fell in love with it. I took one look at it and said, this is a museum. They built it as a museum, only they didn't know it at the time. It was filled with 300 purple cubicles for Silicon Graphics. So I wanted to buy it. The only problem is it cost $25 million that we didn't have. So I went to our board and said, I want to borrow $25 million. It was a crazy notion because many of the people on our board had been on the board of the Boston Computer Museum, where they had failed raising less than $1 million to retire their mortgage. And here it is, I was asking, with no support for the notion that we could ever pay it off, to borrow $25 million. Well, somehow they let me do it. It turns out in retrospect to have been a brilliant move, accidentally brilliant. That $25 million property now is probably worth about $250 million. And we own it. We don't have to pay rent to anyone. So we moved yet again. Now we had decent forklifts. This is the Cray 2 being moved off the truck into the Shoreline building. We created version 2 of visible storage. Again, a lot of computers without a lot of labels. We didn't have the money to build exhibits yet. But we did other things too. We had all this great space. We had lots of volunteers. We started restoring old computers. Upper left is an IBM 1620. Upper right is the first computer from Digital Equipment Corporation, PDP-1. Lower left is an IBM 1401 installation with 2 running 1401s. And lower right is the world's first hard disk, the RAMAC, designed in 1955 by IBM at their San Jose Research Center. With the exception of the 1620 on the upper left, all 3 of these are still running, and we operate them and demonstrate them to the public all the time. Here's an example of a crowd watching the 1401 system being demonstrated. We also demonstrated really old computers like this Babbage difference engine that I described earlier. We cranked it every day. It worked perfectly. We were off and running even though we didn't have permanent exhibits. We reinstituted the Fellow Awards that had started with Grace Hopper in Boston. This is the 2008 Fellow Awards with Gene Bartok, who was one of the original ENIAC programmers, and Bob Metcalf and Linus Torvalds. I'm sure you know those names. One of the things we started with high priority is to do video histories, videotaped oral histories of computer pioneers. We're losing them at an incredible rate. If you don't get them on tape now, they're going to be lost forever. Nobody ever interviewed Alan Turing. There is no video of Alan Turing. So by now we've done about 1,000 oral histories. They're all long videotaped, multiple hours. This is one from Paul Lawton. You may not know that name, but he was the fellow who wrote the DOS, disk operating system, for the Apple II. The one on the bottom is John Backus, a few years before he died. He was the inventor and implementer of Fortran, one of the first high-level computer languages. We started writing blogs. We started collecting and releasing source code. So the blog on the left describes the release of Apple II DOS source code. Source code is the literature of computing, and if we don't preserve it, we've lost a lot of our history. We did public programs. We did interim exhibits, waiting to be able to raise the big bucks for doing our permanent exhibit. We posted lots of videos online, both new videos, like the presentation that Paul Barron, inventor of packet switching, did for us, and historic films like UNIVAC. All of these films are up online. If you go to youtube.com/computerhistory, you can see them all. We instituted educational programs. The educational programs were about, I would say, 20% history, 80% new tech, but it is a way to experiment with the idea of inspiring kids with a combination of what's happening now and what happened in the past. We eventually ran out of space in our building and knew that we were about to, or wanted to, create a big permanent exhibit. So we bought another building over in the East Bay, where real estate is a little bit cheaper. We bought a 25,000 square foot warehouse for storing all of the stuff that's not on display. Like every museum, what you can put on display is a small fraction of your collection. And if you want a really cool experience, talk to me sometime. I'll be getting a private tour of our warehouse over in PS. We'd finally raised the money to be able to build our first new permanent exhibition. So it's called Revolution, the first 2,000 years of computing. It's a big exhibit. It covers everything from pre-computing calculation to the internet and the World Wide Web. This is the mini computer gallery. It's designed for not just the geek, but for the general public who's interested in where computers came from. Everybody these days is a computer user. Gets pretty high marks. It's big. It's got 19 galleries, 1,500 objects, 5,000 images, 16 films, 4 theaters. It's been a great success. We opened it in 2011. In 2015, we wanted to do more exhibits. We were running out of space again, so we bought our third building. This one is a 50,000 square foot building in the East Bay for the archive, which is paper, software, video. It's where we do scanning of documents and films and photographs. It's where researchers come to visit to use the archive. It's where we recover old software. Moving stuff into that building gave us the opportunity to take its space in the main building and create a software exhibit. This is a very different kind of exhibit than anything we've done before. It has history in it, it has technology in it, but it's as much about the social impact of the technology and where it might be going as the history. It's a case study kind of exhibit. So it's an experiment in doing different kinds of exhibits for different audiences. So a brief summary of the museum in numbers. This is, of course, before COVID-19. We are, like all museums in the world, closed, but we were getting 130,000 exhibit visitors a year. Probably as many who came for events, both ours and rental events. We now have 144,000, it's probably now up to 150,000 objects in our collection. Got 75 employees who are still being paid, even though they're working from home, and 200 volunteers. And we raised a bunch of money to make this work. We are, of course, struggling in this period when we're closed, like all museums, but we have a pretty good chance of surviving. We have assets. We have a $30 million endowment. We started this museum with the idea that we are creating an institution that will live in perpetuity. And I don't know whether we've done that or not. I'll know, somebody will know 50 or 100 years from now. I won't be here to know, but hopefully it will happen. And I should point out that after 25 years, I've decided to step down as chairman of the board, and new administration will be taking over. And I think the museum will be in good hands for moving into the future. It's been an amazing journey, but remember, as our exhibits designer Kirsten Tashev taught me, a museum is not about objects, it's about stories. So I want to end with another story that we tell in the museum, and I think is important for people to know. It's about the memory that made computers work. By the end of the 1940s, everybody knew how to build computers. John von Neumann had described, maybe not invented, but had described that the right way to do it was to have enough memory so that you could store the program in memory as well as the data. The question for the engineers is, what do you build that memory out of? Here are some of the examples of things that early computers used to store memory. On the top left is a rotating magnetic drum. It's mechanical, so it's slow. It's also relatively unreliable. On the lower left is a mercury delay line. That's the main memory for the UNIVAC 1 computer. It's 18 tubes of mercury with a speaker basically at one end and a microphone at the other end, and you induce standing waves in the tube of mercury, and you could encode 1,000 bits of information stored that get recirculated around. So this is 1,000 18-bit words. That was the entire main memory of the UNIVAC 1 computer. Expensive, unreliable. If you stamped your foot next to it as it was running, it would disturb the standing waves in the mercury and induce errors. In the middle is the Williams-Kilburn tube, which is basically a TV screen, old cathode ray tube, where you would paint dots on the screen, and the thing that's folded down would be folded up, which is a screen that would detect when a spot on the screen was illuminated, whether there was a dot there before. So it was a destructive readout system, but it was entirely mechanical. You could store 1,000 bits on the face of the screen. It ran at electronic speeds, and it was the memory that was used for the first machine that ran a stored program. It was June 21st, 1948 at the University of Manchester, in a machine called the Baby. It was a 17-line program, the first piece of software ever to run inside memory. The thing on the right was a very complicated device designed by RCA, which was basically a plasma tube where you would store on plasma bits of information. Very expensive. They barely ever got it to work. It was the memory that was initially stored on the Joniac computer. Now notice that 3 out of the 4 of these, all except for the Selectron, have the property that you're not building any specific thing for a bit. That seemed like a good idea. It seemed too tedious to have to build something specifically for each bit. You depended rather on a bulk analog property of magnetic materials or an electrostatic screen or traveling waves in a tube of mercury. None of these were the things that made computers work. But what made them work was a return to that original idea of building something for every bit. It was magnetic core memory. It was one of the things that I brought in as a show and tell item. This is the world's first magnetic core memory. It's from the Whirlwind computer. This is a core plane that has 1,000 bits. You put 16 of these core planes together, you get 1K 16-bit words. And that's the way all computers worked for the next 25 years. Let me reshare my screen here. So how does core memory work? Well, it's based on an old principle of hysteresis that dates back to the late 1800s. Basically, certain magnetic materials, like a ferrite ring, have the property that as you increase the electric current, which is to say the strength of the magnetic field, pretty much nothing happens for a while, until suddenly it snaps and the magnetism changes from one direction to the other. And then you can do things in the other direction, and you continually change the saturation, nothing much happens, and then suddenly it snaps into the other direction. And by the way, once it's snapped, it records that information forever because it never gets demagnetized unless you put a magnetic field on it. That core plane I just showed you might have an encoding of a program for the whirlwind that's 65 or 70 years old. Okay, so how do you address this memory and how do you create a practical memory out of it? You can't afford to put wires through every core that are individual. Well, there are two clever ideas. One is, because of the way hysteresis works, you can put half of a current through a core and nothing happens. So you can have one wire that goes through in the X direction, multiple cores, one wire that goes through the Y direction through multiple cores, nothing happens, and only one core will switch because it gets current from both wires, gets over the threshold for the hysteresis curve, and the magnetism will switch. So how do you know that it's switched? Well, the switching magnetic field induces an electrical current. You put a sense wire through all of those cores, and then you can sense when the addressed core has changed magnetization. So that's the principle on which a single core plane works. This is 1 bit of a 16-bit memory, main memory for a computer. It's destructive readout, notice, so that once you've read out the core, if it was a 1, it is now a 1. If it was a 0, it's now a 1. So whatever you've done, when you read it, you have to rewrite it. Clever idea. Cores got smaller and smaller. It was used for all computers from then until 1972 or 3, when Intel came out with the first semiconductor memory. Okay, so great invention. Who invented it? It's a similarly complicated story to the inventor of the computer. Here's one person who contributed, and this is a delicious story because Frederick Vey was a sidewalk and street inspector in Los Angeles, and he moonlighted in his kitchen laboratory on magnetic materials and how he might use them for electrical purposes. In 1947, he patented something called a memory transformer. It was basically a transformer that would remember its prior state, and it worked. And when IBM got around to wanting to use magnetic core memory, they purchased the patent, the rights to that patent from Vey in 1956. Well, that wasn't the only invention. An Wang from Harvard and later from Wang Labs in 1949 patented the idea of destructive readout. That patent too was purchased by IBM. IBM knew that this was the way to build computers. Another interesting story, by the way, is that IBM was very late into the computer business, but once they got into it, they came in with both feet and dominated the industry relatively quickly by adopting new technology like core memory. Third fellow, Jan Reichman from RCA. He was actually the guy who had invented the Selectron, but he also worked later on core memories, and in 1950 patented the notion of coincident current. IBM licensed that patent as well. Contributor number 4, J. Forrester from MIT, in 1951 patented something that's very much like Reichman's patent, not exactly the same, coincident current. IBM needed that patent as well, but IBM was unwilling to license it. What they said was that we will license you for a royalty of 2 cents per core. That was anathema to Tom Watson. He refused it, He went to court to try to invalidate their patent on the basis of Reichmann's patent, and that court fight went on for years. Eventually, IBM lost. They had to license that patent in 1964 from MIT for $13 million, which was the largest patent settlement in technology at the time. It was a traumatic event for the computer industry because it made engineers realize that the technology they use and the patents that exist on them are extremely important. It was also frustrating to people like Jay Forrester. I love this quote. He said, "It took us about 7 years to convince them that was a good idea, and the next 7 years in the patent course to convince them that they had all not thought of it first. Success has 1,000 fathers, but failure isn't often. So if you have a successful idea, you better be prepared to protect it." Jay Forrester was our second fellow of the Computer Museum in 1995, and he died relatively recently, 2016. The computer that Forrester worked at MIT was called the Whirlwind computer, and it was coincidentally the computer that Gordon Bell wanted the Smithsonian to collect. And since they refused, he decided to start a computer museum. So in some ways, the core memory story and the Whirlwind story are all linked together in the history of the museum. It is still a work in progress. One of the projects we're working on now is reading the old Whirlwind tapes. We have about 150 of these magnetic tapes that were recorded on Whirlwind that haven't been read for 50, 60 years, something like that. We are beginning to read them now. I developed a software-based recovery system for data from magnetic tapes. We basically digitize the analog signals coming off the head of the tape, and then in software reconstruct the bits, the original data, and the software that was running on these machines many, many years ago. If you're interested, by the way, all of my software is up on GitHub, and you can take a look at it at the link there. So it's been an amazing odyssey, lots of lessons to be learned. One about history. When I was a kid, a student, I wasn't that interested in history, but I've obviously gotten really interested in history now. It can be inspiring. You can learn from it. David Kennedy in the history department at Stanford said, "It's an imperfect but indispensable guide to the future." Look, if all you know about is the present, that's a single point, you can draw any straight line to the future through it at any angle. If you understand history, at least you have some other points. You can do some curve fitting. You can do some prediction about what is likely in the future. You can learn about what things were tried and failed. The other lesson for me was, don't be afraid to do something new and unusual. I knew nothing about museums, and I was able to succeed. That won't always happen, so you have to be prepared to fail. But it was a great odyssey, and I encourage you all to be bold and try things that you don't know how to do and might fail at. That's all. It's a little disconcerting to be doing this without a live audience, so I can't get any questions, but if you have any questions, feel free to email me. The email address is there. Of course, visit the Computer Museum at our website, computerhistory.org. There's lots of material there, lots of historic material. Visit the YouTube channel where we have thousands and thousands of videos up there. Come visit once we open again. If you're interested in more of my thoughts on the history of the museum, I have a couple of links there to papers I've written. So enjoy history, enjoy the future. Thank you.